Hey, welcome back, guys. It's Algebra 2, Day 1. We're going to talk about complex numbers. So, welcome back with a little picture here. School is where you learn stuff. Yeah, it's kind of important to pay attention in school. You never know when you're going to need to spell something correctly, or maybe add something. Okay? So today we're going to look at complex numbers. Okay, and complex numbers. So what you do if you have had a chance to download the resources from the digital session is this is on page 1. The cover page is a calendar of events that are going to go on, shows you when your quizzes and tests are. And so this is page 1, and we'll be using page 1 quite a bit here. So complex number is a way to write a number in the imaginary number set. So in previous math classes, you have had opportunities to take square roots of numbers. And what you may remember is that you were kind of told that you were never allowed to take the square root of a negative number. And so what we're going to do, first thing we're going to do in Algebra 2 is show you exactly how to take the square root of a negative value. Okay? And so that's where the imaginary number comes in. Okay? And so our imaginary number is the letter I, used just like it, it's just a variable. It does have meaning, much like pi, but the letter I is used, obviously, for the reason of the word imaginary. Okay? So as we get into this a little bit more, you'll see where the use of a plus bi as the complex number gets written. But for now, what we're going to do is we're going to talk about how do we, hang on, I gotta erase, how do we take the square root of negative numbers? Well, what is a square root, right? So a square root is a number times itself, or a perfect square is a number times itself. So a square root is an operation that undoes that number times itself. So here on problem number 1, let me get the pen. On problem number 1, you'll see that it is the square root of 16. But it's not really the square root of 16, it's the square root of negative 16. So think about that. What number times itself will give you a negative value? Well, if you use 4 times 4, you'll get a positive 16. And if you use a negative 4 times a negative 4, you still get positive 16. So what value times itself will give you a negative 16? Well, in the real number set, it doesn't exist. So we are introducing the imaginary number. So today, erase. Today, we learn exactly how to do that. So we know by talking just a second ago that the square root of 16 is 4. So the way we're going to rewrite this now with the imaginary numbers is we're going to rewrite it as the square root of 4. Actually, no, we're not. We're going to redo that. I'm sorry, guys. We're going to write that as the square root of 16 times negative 1. Because, well, 16 times negative 1 is negative 16. So what we've done is we've broken it down into factors that multiply to give you 16. And that's where this comes in. Let's change the color. That's where this comes in. Oops. I is known as the square root of negative 1. So down here, we get back down here to our problem. What is the square root of 16? Hopefully everybody's yelling at me that it is the number 4. Okay? And then we have this negative 1 right here. Well, if you'll look right here, here's the square root of negative 1. So the negative 1 square root is actually equal to I. So I'm going to change color just to emphasize the fact that the negative 1 here becomes, let me get this in the right spot, the letter I. And so we get a direct, right from the negative 1 right here, this is what turns directly into the I. And so therefore, the square root of negative 16 is 4I. And the I part means imaginary. So we're looking at something that actually does not exist. There is no number times itself that will give you negative 16. So we've kind of made it up, okay? All right, so let's move on to number 2. Another perfect square, okay? So it's 81. So I'm going to write it as the square root of 81 times negative 1. Okay, so square root of 81, that is a good old 9 because 81 is a perfect square. And then what is the square root of negative 1? As we see right here, that square root of negative 1 is called I, the imaginary number. Okay, so the nice thing about problem number 1 and number 2 is that they had perfect squares. Negative 16, negative 81, those are both perfect squares. But now we're going to transition into values that are not perfect squares. Not perfect squares. So I'm actually going to type, oh, come on. I'm going to type up here for you for a second. Our strategy is going to divide I, 2, 3, and 5. Oh, we'll do this. 5, and then we'll put dot, 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 because we can keep those values going until we find the largest perfect square. Our goal is to find the largest perfect square. I'm going to make this a brighter color so we can see that that's standing out. So we're going to divide 45, 3, and 5 by 40 into 45 to see which one gives us a perfect square. So let me pull up calculator real quick, if I can find out where my calculator went. I've not used it all summer. Where are you, calculator? The calculator has disappeared. That's nice. Great. All right, so we'll just do this in our heads. All right, guys. So, pen back. Okay, so let's break apart 45. All right, 45 divided by 2. Does anybody know if 45 is divided by 2? It is, but it gives you a decimal, so we're not interested in that. So 2 is not a good value there. 45 divided by 3. 45 divided by 3 is 9. 9 happens to be a perfect square. So 9 times 3, that is not correct, Coach Scott. 9 times 3 is 27. Good job, somebody caught that. So let's see, 45 divided by 5, that's the 9 I was looking for. So 9 times 5 times negative 1. And the negative 1 is important to be there. Why? This right here. Because it's imaginary. There is no number times itself to give you negative 45. So you got to have that imaginary component. All right, so when we get down here, we are dealing with a non-perfect square. So we're looking at having to take the square root of 9. Take the square root of 9 is possible. That's a 3. So we'll put that on the outside. The square root of 5 cannot be done. So we will call it square root of 5. And the square root of negative 1 is our imaginary component to this problem. So we get an I that goes right there. So we took 45, divided it by 2, 3, 5 to try to find a largest perfect square. Then that largest perfect square was square rooted. 9 square rooted is 3. Square root of 5 is not perfect, so we leave it under the radical. The square root of negative 1 is I, so that came back outside the radical. Moving on to example 4, very, very similar to number 3. All right, I guess we're using red. Square root of 200. So 200 divided by 2. Anybody know what that is? That is 100. What do you notice about 100? That is a perfect square. So 100 times 2 times negative 1. Remember that the negative 1 is a very important component to this problem. So the square root of 100 is a perfect square. So we will call that 10. Square root of 2 is not perfect, so we don't take the square root of it. That's a 2. And the square root of negative 1 is the imaginary component to this problem. So our answers, let's see if I can get this to work, for these 4 problems are 4i, 9i, 3i square root of 5, and 10i square root of 2. So that is how we take the square roots of negative numbers. Okay, so the next step of playing around with complex numbers is understanding that there are 4 values or 4 different versions of exponents for the imaginary number. And so you'll see them here. There's I to the first, I to the second, I to the third, I to the fourth. After I to the fourth, they just repeat. So up here, this might be I to the first, but it's also I to the fifth, I to the sixth, I to the, I to the seventh, I to the eighth, and it rolls back around. This is 9, 10, 11, 12, so on and so forth. All right, so as we get to simplifying the powers of I, what are their actual meanings? Okay, so I to the first is simply just known as I. And that's what you're going to see the most of, is just a normal I, not even going to be an exponent up here. It's just going to be written as the letter I. I to the second value is negative 1. I to the third is negative I. And I to the fourth is just good old 1. Okay? Up here at the top, we have a little saying for you because, yes, we expect you to know these. It's I1 with negatives in the middle. Now, what Coach Scott? What are you talking about? So here, I1. So if you look at these values, what the simplified version of each one of the I's are, it's an I, it's a 1, it's an I, it's a 1. So up here, I1. And then where are the negatives? The negatives of those 4 versions are in the middle. So it's I, negative 1, negative I, and 1. So it's I1 with negatives in the middle. So as we move forward with this, what we're going to ask you to do, if you'll look at the bottom of the page, or close to the bottom of the page, you'll see that the exponents get kind of large. So we have 13, we have a 27, a 54, and a 72. And so, yes, there are only 4 versions, and it's 1, 2, 3, 4, 5, 6, 7, 8, and so on and so forth. But I don't think really anybody wants to anybody wants to count straight up to 72. So what's the strategy? How do we go about figuring out which one of the 4 versions of I represents, say, I to the 27th, okay? So here's our strategy. We're going to divide by 4. Why 4? Because there are 4 versions of I. So let me get my pen back. We are going to divide, divide I'm new at this class pad, so guys, I will get better at this. The exponent by 4. Okay, I found my calculator while you guys were taking a break, and so here are the remainders that we're looking for. 0.25, 0.5, 0.75, and 0, or 0.0. Okay, so those are the 4 versions, those are the remainders for the 4 versions. So let me show you what that looks like on the computer. All right, so if you'll look below this little box, you've got these 4 examples. And so what we're going to do is we're going to take 13. 13 is the exponent, and we're going to divide it by 4. Why 4? Because there are 4 versions of I. All right, so I told you I found my calculator, so I'm going to bust that out. We're going to go 13 divided by 4, and you're going to see that the answer comes out to be 3.25. So back over here, let's see where you are. So that is 3.25. So the important part that we're looking at is the remainder right here, this 0.25. And so what we're going to do is we're going to come back to that chart and we're going to figure out that 0.25 is sitting right here. So therefore, I to the 13th represents, and I overshot, I to the 13th represents the simplified version called I. So our answer to I to the 13th, as we simplify it, is simply I. Okay, so over to number 6. We're going to take 27. We're going to divide it by 4. We're going to see what that comes out to be. Where are you, cursor? Cursor, there we go. So 27 divided by 4 is 6.75. All right. So back here, we were looking at, it was 6.75. Again, the important part is the decimal. This here, 0.75. So you look at the box, it's just above these problems. You'll notice that 0.75 represents negative I. So the simplified version of I to the 27th, pen, is negative I. 54 divided by 4. Calculator. 54 divided by 4. Enter. Gives us 13.5. So that one is the second version. So here's the 0.5. I kind of messed that up. Sorry about that. So 0.5 represents negative 1. So this simplified version is just negative 1. And over here, change the color just for fun. 72 divided by 4. That's a 4. Come on, 4 is, anybody know? No? All right, so we'll go to the calculator. Y'all can yell at me from the from your couches. That's fine. I won't hear you. 72 divided by 4 is 18 with no remainder. There was no decimal to that over here. See, that's just 18. So this was, where are you? Just, oops. Let's try that again. All right, so we have, oh, come on, pen. 18 with no, that's basically 18.0. So that's the 0.0 is what we're looking for. So down here on the bottom, come on, cursor, down here on the bottom, come on, 0.0 is, whoops, .0 represents just 1. So our answer is just 1. And that is how we simplify exponents. Okay, so the final thing we need to get done today is adding and subtracting complex numbers. And so adding and subtracting is treated just like any other algebraic adding and subtracting that you've ever done. So we're going to treat the I like any other variable. So in the addition subtraction of complex numbers, we do need to make sure that when we're done with the problem that it is in the order a plus bi. A is the real part and bi becomes the imaginary part. Notice the I that's hanging out there with the b. So when we get down here to the two complex numbers that are going to be added together, we find the real parts, 3 and 7, we add them together. Pretty simple. That's going to be 10. 2i plus 6i is going to be 8i, and that's it. That is the addition of two complex numbers. And we get to problem number 10, it becomes a little bit trickier. And so we're going to have to make sure that we take care of this subtraction sign that's in here. Now, what you're doing is you're taking 6, there is 6, and you are subtracting the 1. Usually not a problem. So most people will be able to come up with 5 on that. But here's the issue that we have. We see a negative 5i, and we are supposed to subtract 2i. But what most people do is they take negative 5, and they take, come on now, and they take negative 5, and they get 2, and they combine them, which is going to be incorrect. This subtraction sign applies to everything that's in this parentheses. So what I will typically tell you to do, and I'm going to do the best I can here, is change this to an addition problem by changing the sign of the negative 1, or sorry, the 1 and the 2. So this now becomes 6 plus negative 1, which is still 5, and negative 5i minus 2i, which is now negative 7i. Please note that the complex number is always written in the real number first and the imaginary number second. So the I number comes second. Okay, so 8i was second, 7i was second. All right, so let's do that again over here on this one. So we take this subtraction sign and we make it a, whoops, a very poor plus sign. Let's try that again. Plus, we'll change the 2 to a positive as well because it's double negative, and then the 3 is positive now, so it's going to become a negative 3. So what we have is 9 plus 2, well, that's 11, and negative 4 minus 3, which is a negative 7i. Okay, so we have complex numbers 10 plus 8i, 5 minus 7i, and 11 minus 7i. Let's change it up a little bit. All right, down here we have a subtraction sign. That subtraction sign right there goes to everything that's in the parentheses behind it. It stops right here at the 2i, so we don't use it for that negative. So we'll change this to a plus. The 10 becomes negative. The 2 becomes negative. And then you find all of the like terms, which in this case, they're kind of right next to each other. So you have 9 plus negative 10, that's negative 1. And negative 2i, negatives 5i. We got a lot of negative 7i's today, guys. So, so we had another negative 7i out of this one. I don't really like my I. Let's try to make sure that I can tell that you have an I written down. Okay, that's a lot better. All right, last problem. So on this one, you'll see, you'll see that you have an exponent of 4, an exponent of 3, and yeah, so they repeat each other, okay? So we'll find the like terms. Let me get rid of those. All right, so let's find our like terms. We do have a subtraction problem, so let's change this up. We'll go to plus negative 2 and a positive 6. So now we have 11i to the 4th plus negative 2i to the 4th is 9i to the 4th. We have 4i to the 3rd plus 6i to the 3rd becomes plus 10i to the 3rd. All right, we can't leave things in terms of anything except I. So what we saw just a few minutes ago was that there are different versions of I. So we have an I to the fourth, which can simplify down just to a 1. So what you have is 9 times 1 plus 10 times, times, y'all remember what I to the third was? That was negative I. And so basically you're almost done here. 9 times 1 is 9. And then you have 10 times negative I, which is going to be negative 10I. And that is your finished addition and subtraction. Okay, that's going to do it for addition and subtraction. More thing to that. So the lesson itself is fine. But what I forgot to do was tell you that you do have an assignment tonight. Hopefully everything will go well. And by that I mean hopefully CTLS is working and everybody has an opportunity to get into CTLS and download the things that you need to download. Now, you do not have to print out the PDF. If you want to do all of your work on a separate sheet of paper and upload that, by all means, that is completely fine. Please do that. That's what I would do. I wouldn't print out all this stuff because it's just going to cost you money with a printer. Okay, so page 3, numbers 1 through 10 are going to be simplifying your radical. Sorry, it's going to be simplifying your complex numbers, and then page 4, 1 through 14, is going to be simplifying your radicals. So you guys have a good night. I will see you in the live session.